Okay, so in the Crane Lab part 2, what we're looking at is we're looking at the boom of the crane that has been elevated at a certain angle, and I've given you that angle as theta. So we have the boom of the crane at a certain angle, and here I'm gonna condense my boom. I'm gonna simplify it down, and this line represents the midline of that boom. Okay, so we had the joint here, the pivot joint where it was connected to the body of the crane. And we have, I'm just going to draw this as a dotted line right here, but this is going to be just the angle theta right here. Okay, so we had the weight of our boom, and I gave you that here. Let's make this a little bit longer there. Okay, so we had the weight of the boom. Okay, so let's call this force of the boom. Okay, let me look real quick. I actually forget what I called it. We'll just stick with F of B for now. And then right here, I might have called these L on the lab. So L, F, they're both, or I think I called it W on the lab on the picture. But FB is the same as WB, and then F of the load is going to be the same as W of the load. Okay, and then we had one more special force here that we don't know, and this is the force that we wanted to solve for. That's going to be the force of this hydraulic cylinder that we had. If you look back at the picture of the crane, you have a little mechanism coming up and supporting the elevated boom. Okay, so that is going to be the force of the hydraulic cylinder, and I'll just call it FH here. Okay, the FH I had given you, okay, with respect to horizontal, I've given you an angle that the force of the hydraulic cylinder was acting at. Okay, and I called that, I gave you an alpha value, and so for everybody, this alpha value is going to be slightly different. Anywhere from like 22, 23, or 21 degrees are some of them, right around in that range. And then the theta angle was anywhere from, I think, 45 to 50 down to maybe 30 or 35 should be that theta value that you have. Okay, the one last thing about this FH is that it doesn't act directly on the midline of the boom. If you notice in the picture, it's acting at a certain distance away from the boom. And that distance, that perpendicular distance that it's acting right there, is going to be 1.5. Okay, so this force of the hydraulic cylinder is going to be acting at 1.5. This is a distance, 1.5 feet. Right there, from there to there. From the midline of the boom to where that force of the hydraulic cylinder is acting. Okay, and then we also had, I told you that from the pivot, it's acting at 10 feet. Okay, so those two numbers are actually going to be the same for everybody. So that 10 feet and 1.5 feet. The things that are going to be different for different groups are the distance to that center of mass of the boom. And for now, I'll just call that D boom center of mass, so DBCM. Okay, and then the whole length of this elevated boom I called DL. Okay, so this is just the distance to where the load is attached to the boom. Okay, so now that we have our free body diagram set up, we can start converting these forces into the perpendicular component of those forces that are acting. Because if something is causing a torque, you have a component and it's not directly acting perpendicular. You have a component of that force that is either a push or pull force. So let's go ahead and break down. Let me get out another marker here so we can have a different color. We'll use this nice green one. I'm not sure how it'll show up on this blue paper. But okay, so we're going to break each force into its parallel and perpendicular components. So this force of the boom, which is the center, that's acting at the center of the mass of the boom. So this FB was actually 2,000 for everyone. Okay, so FB is that 2,000 pounds. The F load varies for everybody, anywhere from 500 up to 2,000, I believe, are the numbers that I gave for that. So this force of the boom I'm going to break it up into, this is perpendicular to there, and this component right here is going to be parallel to the midline of the boom. So we know that this is actually going to be a right angle as well. Okay, so if we look at any sort of triangle, and back to when we talked about that car on the incline, if you have an elevated angle here, theta, we know that this angle also is going to be theta. If you want further explanation of that, please talk to me in class. But I can definitely show you the trig that shows you that, why that is. But for now, let's just say we know that that is theta. So you know this component right here, this perpendicular component of this force caused by the weight of the boom, which is acting at the center of mass, is going to be FB. Oh, this marker isn't doing too well. FB cosine theta. Because if you have an angle and its side, you're looking at the adjacent side, the cosine of that angle is going to equal adjacent over the hypotenuse. Okay, SOHCAHTOA, so CAH. Cosine, adjacent, hypotenuse. Okay, so we know that that's cosine. And similar reasoning, we can get that that is FB sine of that theta value. Okay, so same explanation here that I just gave to you for the FB. You know that that's a right angle. You know that this is a right angle right here. So you can know that that is theta. Okay, so this is FL sine theta, and this is FL cosine theta. And again, everybody has numbers for FL and theta. So these are actually just numbers. So when you're going through and solving the problem, you can actually find a numerical value for these, and you can find a numerical values for these as well. Okay. So next step here, and this is where it gets tricky, is we need to find the parallel. Well, first off, okay, so there's actually two different ways we can do this. So this force is acting at a distance away from the midline of this boom. So this right here is not the lever arm for this whole force. That lever arm for that whole force would actually be a line right there. Okay, so one way you could do this is you could find, using trig, find this distance of this hypotenuse. This is a right triangle right here. And then break up this force into parallel and perpendicular components of this new lever arm. But that's not how I'm going to do it. I'm going to do it the other way. I'm going to keep in this reference frame that we've established, and I forgot to do this, and that's my bad. That should have been done as one of the first steps here. But I have established my reference frame. Positive x is directly along this boom right here. My 0 point is right here at the axis of rotation, this pivot point. And right here is going to be my positive y. Okay, so all these lengths right here are going to be positive in the x. And then this is going to be a y component, and this is going to be a y component. And these are the perpendicular components that are causing a torque. Okay, so my FH here actually has components, and let me erase this line here so that you guys don't get, yes, I have like a surfer pencil. It's really awesome. Okay, so what I'm going to do is I'm going to break this FH into a component that's parallel to our boom here, our midline of our boom. So that's my parallel component. And this is going to be my perpendicular component right here. Okay? Beware that this is how I drew the triangle right here, but this force actually is acting right here. Okay? So this force right here acts in this location. So let's actually, well, I'll draw a new free body diagram here in a second so that we can see this once we get this all broken down. But what we need to do is we need to actually find what this angle is right here. So we have a new angle that's important, right? Because we know that this is alpha, and this alpha is from directly vertical, okay? We know that if we were to draw this over here, so let's just go ahead and I'm gonna just move this over here. I can't erase because these are Sharpies, but I'm just gonna go ahead and draw this right over here. Okay, so you can see that this and this are the same. We don't have two forces here. So let me just I'll just kind of X this one out with pencil. There we go. So sorry, this is kind of really low tech right now. But if we can actually find, we know that this angle, so anything that's perpendicular right here, we said that it was going to be theta. Okay, so here we have another vertical line. It's not attached to the boom, but we still know that anything with respect to vertical right here that's going to be perpendicular to our boom is going to be that angle theta. So we actually know what this angle is right here because this is perpendicular, that's parallel, so this whole angle right there is going to be 90 degrees. So we know that right here is going to be 90 minus theta minus alpha. Okay, so that is our angle that we're dealing with now. Okay, so we have two sides here, and I just moved this side over here, but to this triangle, and this one is going to be adjacent to the angle that we know. Okay, so this one is going to be FH. These are components of FH, so we got FH times the cosine, because it's adjacent, of 90 minus theta minus alpha. Okay, this side right here, and I'm actually going to just write it, I guess, right? Well, no, I'm going to just draw a line, okay, because bear with me here. Okay, so I'm going to draw a line. So that one right there is going to be FH times the sine, because it was opposite. It's opposite of that angle, and we can just move this vector. It's actually acting right here, so I wanted to move it up, so you know where it's acting. So F sine of 90 minus alpha, or minus theta minus alpha. And again, this alpha and this theta, I gave you those two values. Okay, so you know these. So again, this is just going to be the sign of a number when you're doing it. So don't make these variables confuse you. These are just, this is a number and this is a number. So the only thing we have here that we don't know is going to be our FH. Okay, so we have an FH here, right there, and we have an FH right there. Okay, so I'm going to move on and now sum the torques. So all of these forces are creating a torque about this pivot point. So I'm just gonna redraw this quick because it got really messy really quick, and I think it'll make more sense if I redraw it. Okay, so we have acting right here, we have okay, right there at 1.5 feet away from the boom, we have acting on FH. I need a smaller Sharpie. This one got really fat. Sine of 90 minus theta minus alpha. Okay. We have right here acting right there. We created that one with these are the force of the hydraulic cylinder broken into components parallel and perpendicular. Here we had an FH cosine of 90 minus theta minus alpha. Okay, I really hope you guys can read this. It's got fat. Let me see if I have a small one. Nope, I don't. Okay, we're gonna deal with this. Okay, so we have acting at the center of mass of the boom. We have an FB cosine theta, and acting at the load, we have an FL cosine theta. So this was an FL cosine theta. Okay. Okay, so here's our pivot point right here in this location. We have this, we know our distance. I drew it in the other one, or in the other picture, but our distance there was dBcm. So from here to here is dBcm. Okay, from here to here was dL. So those are both going to give us negative torques, because anything that's going to cause a counterclockwise rotation gives us a positive torque. So let's start our summing of our torques here. So the summing of our torques, we're going to set our sum equal to 0. So we have, well, okay, so the first two that we're going to do are going to be negative. So we have negative dBcm well, crap, just going to get rid of that. Okay. The whole thing is negative. dBcm times FB cosine theta. Okay. So that's this right here. This one is also causing a negative torque because it's causing a rotation this way, or clockwise. So we have negative our force FL cosine theta times our distance. The way I wrote this, it should have been reversed, but it's the same thing if you multiply it together. So our force times our lever arm, this is actually our lever arm, and that's our force. But we have our force here times our lever arm times dL. Okay, and then we have, so now we have our force of our hydraulic cylinder. And our hydraulic cylinder, so we have this component that's acting at 10 feet. Because we said it was a distance of 10 feet right here. Okay, so this component of the force it can be thought to be acting right here. It's equivalent. So this is a force of this value, which is FH times some number, which we get when we put into our calculator, sine of 90 minus whatever theta you have for your group minus whatever alpha you have for your group. So that times 10 feet is going to be the torque caused by this component. Okay? But we also have this other component. And if this force was acting directly on the boom, this force would be just pulling on the end of the boom here and not causing any sort of rotation. But if you pull on something away, a distance away from that axis, it's going to actually cause a rotation. So if you're pulling in this direction, parallel, you can think of it as this force right here acting at a lever arm right here of 1.5, because we know that was one of the distances I told you. So if you visualize this instead, just move this vector over here, it's pulling at a distance from this pivot point, and you can, and I gave you that value. It's 1.5 because this is now, well, I gave you that. That's the value I gave you. I said it acted a perpendicular distance from the center, the midline of the boom of 1.5 feet. Okay, so this is going to cause, if you were pulling right here, that's going to cause a clockwise or counterclockwise rotation. If you push right here, that's also going to cause a counterclockwise rotation. So now we have two other components, other forces that are causing a positive torque. So those torques, when we add them into our equation here, are going to be positive. So we have positive plus F, or well, let me draw this, since this is what we need to solve for. We have a plus FH. So this is, I'm going to start with this force right here. So we have FH times sine 90 minus theta minus alpha times the distance of 10. And then we also have plus F8. Oh, I forgot. That's supposed to be red. My bad. Oh, and it came down. Plus FH times, so now it's this component right here, times the cosine of 90 minus theta minus alpha. And then this one is going to be multiplied by 1.5 is our lever arm right there, 1.5. Okay, so in all of this big long equation, this all is equal to 0. So we're basically there now. So now you have your whole equation here. Let me kind of move it so you can see the whole thing. Okay, so you can factor out an FH here, and you'll have an FH parenthesis. You have the sine of 90 minus theta minus alpha times 10 plus, inside your parentheses it's a plus, so plus cosine 90 minus alpha or minus theta minus alpha times 1.5. So, and once you do that, you have your FH. You can add both of these to the other side, and you can get an equation in terms of FH. So let me write that equation in terms of FH, and you look at it and see if it makes sense to you, the algebra that I took to get there. And if it doesn't, this is another thing I would like you to come talk to me in class about. So if we solve for our FH is going to end up equaling, okay, we have, where did my blue Sharpie go? Okay, here it is. So FH equals dBCM times FB cosine of theta. Okay, and we have a plus. Notice both of these are minus, and it was all equal to 0. So what I'm doing is adding them to the other side. Plus FL cosine theta DL. Well, shoot, I still kept this the wrong way. It should be FB cosine theta times dBCM. Regardless, it's going to give you the same number, but I like to be consistent with force times the lever arm. Okay, and then you're going to divide all of that by this term that I was talking about up here, that when you factor out the FH. So what that's going to end up being is 10 times sine of 90 minus theta minus alpha plus 1.5 times cosine 90 minus theta minus alpha. And again, I know this looks ridiculous because there's so many variables, but the only variable you didn't know was this. At this point in the problem, you plugged in everything, and these are all just numbers that you found using your calculator. So this is the formula, per se, of how you would figure out what your force of that hydraulic cylinder is. And I did say this at one point in time, this is not the only way to find this. This is only one of a number of methods that you can do, that you can use. But it would be a good idea to check. Again, I have all the numbers that I calculated for the force of the hydraulic cylinder. So once you calculate it, if you followed on the video, you should be good. If you used another method, it might be a good idea to double check with me the number that you got, so that we can see what you did and make sure you're understanding. But yep, this was the problem, and I know it looks complex, but what I care about is that you understand why we broke up these forces in the way that we did, and why we use these lever arms in the way that we did. So you can watch this as many times as you want. I know it's definitely what you want to be doing all weekend and probably all next week, because it's so entertaining. But thanks for watching, and I will see you guys in class.